we don't have to have the light coming at this angle. Maybe it comes in at a bigger angle. So let's try a bigger angle. If I were to draw it, it looks like this. Comes in, and of course it's going to get bigger. So maybe now it goes this way. Okay. Well, as you can see, eventually the outgoing light is getting closer and closer to the surface. And so the question is, well, what happens when it gets to the surface? So let me draw a line. Let's say this line here, this is light coming in, hits the surface, and this time it skims the surface here. This red line is coming in at what's called theta C. Theta C, I will call the critical angle. And what it represents is for whatever material we're starting in, water for this example, if I shine light from the water going towards the air, at this angle, the light actually doesn't make it to the air. So if someone is outside, let's say you're in a swimming pool, someone's outside looking towards you and you're shining a light, flashlight or a laser at this angle, they won't see the light because the light doesn't leave the water, it skims the surface. That's called the critical angle. And it's critical because if you go bigger than this angle, so I'll do that, let's say in this kind of cyan color, bigger than the angle, it actually reflects back down now. So this angle, bigger than the critical angle, means total internal reflection. Okay. And something smaller than this critical angle, like the gray and the green lines, the light does escape into the air. Okay, so for all of these, the angle's changing. Just like before, it's still refraction. Here, because we're going from a more dense to a less dense medium, the angle gets bigger. But because of that, there's a chance that since the angle gets bigger, that you could shine at a particular angle whereby the light doesn't leave into the second material, but skims the surface. That very particular angle is what's called the critical angle. Any angle bigger, the light actually reflects back as if it's a mirror. Any angle smaller, it leaves the material into the second. So this is very nice. As we discussed last time, things like fiber optics are allowed now. It's a big technology we use nowadays for a bunch of things, mostly communication, audio, data signaling, but also decorations and fancy stuff like that. So because we know this exists, we may want to find out, okay, if we have a particular material, I want to know, what should this angle be? How should I shine my light to ensure that the light does reflect back? And so that is called, let's say, as an example, calculate the critical angle for glass or any material we're talking about. When I ask this question, what you should assume when you read it is, I mean, the light will start in the glass and go to the air. Okay, I don't say specifically it's going from glass to air, but if I talk about the critical angle and I give you material, well, assume the other material the light is going to is air. So if I draw it, here's the picture. Down here is glass. Up here is air. And the light is going to come in, and I'm going to force it to come in at the critical angle. So the light's coming in at the critical angle. And what I'd like to find out is, what is that number? What is the critical angle? Well, one thing I know is that if it's the critical angle, then the light skims the surface. Okay. That also tells me theta 2, which is the angle that the light would be at in the air, this angle here, theta 2, of course, is 90 degrees. Because here's your vertical line, there's the light horizontal, that's a 90-degree angle. So to calculate it, I set up Snell's law, just as before. N1 sine theta 1 is N2 sine theta 2. What's my 1 stuff? I'm starting in the glass. My 2 stuff, I'm going towards the air. So I calculate my stuff. N1, the glass, 1.5. Sine of theta 1. What is theta 1? Theta 1 is the angle the light's making in the glass, which is called the critical angle. So that's the thing I'm trying to calculate. Right side, N2, that's the air stuff. So N2 is 1. What's theta 2? Well, I just showed theta 2 is 90 degrees, and this is always true. If what you're doing is calculating the critical angle for a material, then that forces theta 2 to always be 90. So theta 2 is 90. And now we have Snell's law for this. Just like before, no difference. Up here, N1 sine theta 1 is N3 sine theta 3, a whole bunch of numbers with an angle. Same thing here. The difference is, it looks a little different only because instead of looking for theta 2, I'm now looking for theta 1. And I just call it something fancy. Instead of calling it theta 1, I call it critical angle. So let's solve for it. Theta c is inverse sine, just as before, of 1 over 1.5 times sine of 90. And so I can plug this in my calculator. And when you do, you get an answer of 41.8 degrees. So if you happen to shine light in glass going towards the surface, towards the air, at an angle of 41.8 degrees, the light will skim the surface. If you shine it at a bigger angle, like 50, the light will reflect back down into the glass. If you shine it at an angle smaller, like 30, it'll leave the glass into the air. And that's critical angle. Any critical angle problem I give you will be just like this. I will say, calculate the critical angle of blank. So in this case, it was glass. Last class, we did water. It could be any material as long as you know the index of refraction. And also, remember that this only works when you're going from a more dense medium to a less dense medium. So if I tried to do it from air to glass, it doesn't work. There is no critical angle when you go from a less dense medium to a more dense medium. The reason is because if you go from less dense to more dense, your new angle is smaller than your starting angle. So you can never shine light at an angle that'll give you a theta 2 of 90. Because if theta 2 is 90, theta 1 has to be bigger than 90. But you can't shine a light bigger than 90 degrees. So you have to go from a more dense to a less dense medium. That's what we did here. We went from glass to air. Or we could do from water to air, for instance. Now also note, a second thing is, you don't have to go from something to air. You could ask the same question, but instead say calculate the critical angle for light going from glass to water. Okay. How will this be different? Almost no difference whatsoever. The only difference is that instead of the 2 stuff being air, it's now water. So where you saw N2 is equal to 1, N2 is now equal to 1.33. Theta 2 is still 90. It's still a critical angle problem. All the stuff on the one side is the same because it's still glass. So literally the only thing that changes is what value of the index of refraction do you put for N2. So this is nice. Whole bunch of questions can be asked about what seems to be a fairly complicated phenomenon, but they all, at the end of the day, are Snell's law with the special case of theta 2 being 90, and you're looking for theta 1. So any questions about the critical angle?
So what with the other problem that we did, what's the difference from that one and this one? Because this one only has like one angle and the other one it was like two different ones and then the whole one made up that one. So
Yeah,
like
good.
what's the difference?
Yeah, it's different because for any of these, all refraction problems, and then critical angle is a special part of refraction. Every refraction problem at the end of the day is something like this. You have two materials, material 1 and material 2, and light is coming in and doing something, right? Now, it can be complexified, which is what our first example was, by saying, well, instead of there just being two materials, maybe there's three. So you have 1, here's 2, and then there's a third one down here is 3. But still, you have light coming in, and it comes in here, and then it goes out here. So now you have theta 1. Well, here you had theta 1 and theta 2, and N1 and N2. Here you have N1, theta 1, N2, and this is theta 2, and then N3, and this is theta 3. And of course, we can have more. We could have 4 layers. We could have 15 layers. It doesn't matter how many layers we have. No matter how many layers we have, we're still doing the same thing. You're going to have N1 sine theta 1 is equal to N2 sine theta 2. That's for this, and that's for this. However, for the one on the right, because there's a third material, once you do this, then you have to go from the second material to the third, because all you've done here is gone into the second material, but the light's still moving. So now you have to have another one, N2 sine theta 2 is N3 sine theta 3, because now the light has to get out of the second material and into the third. And then, like I said, if we have a fourth material, then we need another one. N3 sine theta 3 is N4 sine theta 4, and so on down the line. So for the first example we did, I just happened to pick, a complex system with multiple layers. The regular problem will just have the first 2 layers, which is like this example over here, where we just have one Snell's law thing. Critical angle is just like the one on the left. You only have 2 layers, air and glass or air and water or whatever it is. You're going from one layer to the other. Whether we call it critical angle or just a normal refraction problem, they're handled the same way. You use Snell's law. What you're looking for is different. With the refraction problem, we're looking for theta 2 probably. And with critical angle, we're looking for theta 1. And we know theta 2 is 90. If, however, we then do the more complicated question with 3 layers, we're still looking for a theta. Maybe it's theta 3. And so you're just using Snell's law to get theta 3. You could either do, multiple sets of Snell's law to get you all the way to theta 3. So you do the first one to get theta 2, and then you plug theta 2 into the next one to get theta 3. Or you could do the little shortcut thing and just go theta 1, 1 stuff is equal to 3 stuff. Okay, so they're all different in some way. Some have more layers, some have only 2 layers. Some you're looking for critical angle, some you're looking for angle of refraction. Every single one of them is set up the same way. Snell's law is the equation. You plug the stuff One of the things you don't know, solve for that one thing. Okay, so it's very, very similar. This one on the right looks a little different because of the third layer. So we have that extra equation. You have 1 to 2, that's one equation. And then you have 2 to 3, that's your second equation. If you do it that way. If you don't do it that way, then you just have 1 to 3 and you skip 2 altogether. And you get the same answer either way. Okay, so does that make sense?
I think what I'm really trying to ask is what's the difference in finding the critical angle and finding the like the refraction, the total.
Yeah. I see.
Yeah.
They're all angle of refraction. Okay, so critical angle, well, I'll put it this way. Angle of refraction is the angle that the light makes when it goes into a second material. Okay, so you have let's say the angle of incidence. That's what is the angle of the light when it's coming in, the very first angle. Incidence because it's coming in. And an angle of refraction is the angle theta 2, the angle going into the second material. Critical angle is the opposite. Critical angle is the angle of incidence. It's the first one, but it's a special version of the first one. Theta 1 is the angle that light makes in the first material. If that angle is the special angle where it forces theta 2 to be 90, the angle of refraction is 90, then we rename theta 1 and just call it critical angle. We give it a special name because it's a very, very special angle. But if it's not the critical angle, then it's just called theta 1. Angle of refraction is what we call theta 2. That's the angle that the light's making once it gets into the second material. So when you're reading a question, you're either going to get a question that says light is incident on the surface of a pond at an angle of 30 degrees, calculate the angle of refraction. That's telling you, okay, I'm going from air to water. Theta 1 is 30 degrees, and I'm looking for theta 2, the angle of refraction. Another question you can get is calculate the critical angle for water. That is, I want to find theta 1 in water when my light is going to the air. So I'm going from water to air. So theta 1 is the thing I want, and theta 2 has to be 90 because I'm asking about the critical angle. Okay, so does that clear it up a little more?
So you said it's always going to be 90 degrees for the angle 2 for that one?
If it's a problem asking about the critical angle, then theta 2 is always 90. That's the special case. That's right. And like I said, if you don't remember it, if you draw the picture, you'll realize it fairly quickly. Because if you're at the critical angle, the angle coming in is the quote unquote critical angle, that means the light skims the surface. So if the light's skimming the surface and we want to know what is the angle with respect to this vertical line here, well, that's a 90-degree angle. Thus, theta 2 has to be 90. And so, yeah, anytime it's a critical angle problem, theta 1 is the thing you want, theta 2 is 90 degrees. If it's the other way, if it's the normal refraction, then you're given theta 1, you're told, oh, the light's coming in at 30 degrees, but you want theta 2. You're asked for the angle of refraction. Okay?
Thank you.
Sure, sure. Any other questions? All right, well, that's it. That's all the material for the semester. We're now done. No new stuff's coming. Number one, on Canvas, as has always been true, there's the previous lectures that were posted from last year that you could watch for, if you want to hear me explain it maybe in a slightly different way. And some examples worked in there. Also, practice problems are posted on Canvas with the solutions, so you can see how they're worked out and make sure you get a good look of what the questions look like that you'll probably be seeing on the test. Also, I will be posting a homework assignment about this refraction stuff, or it may have already been posted. I don't really remember right now, but I'll check to make sure. If it's posted, of course, it's on Canvas, and I'll send an email about it. I already posted it, you said?
I was wanting to know if possible, could you scroll up, please? I was
yeah.
trying to no, like the other way.
This way.
Yes, sir.
To where do you want? Is this fine?
Yeah, a little bit more, please. Okay, that's all I needed. Thank you.
Sure. So look out for that homework assignment. Wednesday, we will have a test review. So I'll go back over all the topics we discussed in optics. Any questions you happen to have, any problems you want to see worked out, any examples, come in with them, and I'll be happy to work out as many examples as you want to see. Friday will be the test, just like the previous test, posted on the Canvas. Download them, work them out. You'll have the full day to work on them, and turn them back in by midnight that night. And then Monday, which will be our last class, will be the final exam review. Now, of course, if you already want to start working on studying for it, you know, it's a cumulative exam. So it's on all the topics we've discussed. Likely, if the problems showed up on tests, those are the types of problems I'm find more important. So those types of problems will probably be on the final exam as well. So keep that in mind when you start looking ahead at that. And then, of course, final exam during the final exam time. So unless you have any questions, you are free to go, and I will see you on Wednesday.
I have a question. Oh, sorry. You can go, Leah.
I know that the finals exams are set to be in person this semester, but for your class specifically, are you going to do it in person, or are you going to just make ours online, like the whole class?
I think I'll go ahead and do it like we've been doing our tests, just because that's what you're used to. And I don't know if, how many of the students have been, are not able to come in for whatever reason. So I think the easiest for everybody would be to just handle the final exam like I handled the rest of the tests. Now, if for whatever reason you have an objection about it, you can, of course, email me and let me know, and we can discuss how to resolve it. But yeah, I was planning on just handling the final exam as we handled the mid-semester tests.
Okay, thank you.
Dr. Roskin Smith.
Yeah.
I'm a graduating senior, and our final is next week, or our finals are this week. So
Okay.
Is there any way I can take my final exam this week?
Yeah, no problem. So what I would do, anybody who's a graduating senior, please email me, let me know. And yeah, I can have the final exam set up and ready to go for you so that we can get it taken care of as quickly as possible, for sure. Just email me,
great.
we'll get it all set up.
Great, thank you so much.
All right, no problem.